I know, right? Remembering how to write.
Yeah, it looks so bad.
Nothing was working for me my first class of the day. And eventually I could put it all the way right on the board, and it's like, it's been so long since I had to do this. But it was, my penmanship was okay. I think it was alright. Which is always a feeling.
I'm used to like typing from like doing stuff. Yeah, so
I bet. Alright. So chapter 1, just kind of a icebreaker, get your feet wet. It has nothing to do with statistics. We're just talking about number and algebra basics. So section 1 is just the types of numbers. So, our sets of numbers. We have the natural numbers. Those are the counting numbers. In mathematics, the natural numbers sometimes will include 0 and sometimes will not include 0. In the IB course, we're including 0. Depends on the math convention or the course that you're in and the convention they're using. Here we're counting 0. You should be familiar with like these characters. So this is the abbreviation for the set of natural numbers. This is the abbreviation for the set of integers. Those symbols you should be able to recognize if they should appear on printed on a sheet of paper like a homework or a quiz or a test. So the natural numbers, just your counting numbers like 0, 1, 2, 3, 4. They're only positives. They're all whole numbers. No decimals, no fractions, unless you write something like 2 over 1 or 4 over 2. It's like, okay, well that's still a natural number. Everybody feel good with natural numbers? Integers are the natural numbers and the negatives, or negative versions of them. So like -3, -2, -1, 0, 1, 2, 3, etc. Integers. No decimals, no fractions unless it's like 4 over 2 or something, right? As an additional piece of notation, sometimes we'll write z plus. That's the integers that are greater than 0. So that's 1, 2, 3, 4. Or we might write z minus. That's the integers that are less than 0, -1, -2, -3. Everybody's okay? Difference between n and z plus is got nothing. 0, right? N includes 0, z plus does not, right? Z plus is strictly positive, and also, so 0 isn't in there, but it is in it. Everybody's okay? We okay on this slide? Fairly straightforward. Yes, sir?
So n is never negative?
Correct.
Okay.
No negatives in n. Yes, sir.
So it's like 4 over 2, like a natural number.
We would count it as a natural number because it can reduce down to.
And z plus.
Yes. Would be in z plus, and n. Yes. And now you're getting into something that sounds like a test question, right? Where I give you a number and I ask you, what are all the different sets that number is a member of? Right? Okay. Next set are the rational numbers. We use that letter Q to represent the natural numbers. The definition for our natural numbers is anything that can be written as the quotient of 2 integers, where the denominator is not 0. So like 1/3, rational number. But so is some decimals. What kind of decimals are also going to count as rational numbers? There's 2 major types. Is 0.25 a rational number? Can you write it as a fraction?
Oh,
Yes, what fraction is it? 1/4, right? So what's special about 0.25 that immediately tells you can write it as a fraction? How about?
It's a quarter of 1.
Okay, what about 0.123? Can I write that as a fraction?
Yeah, but it's like bigger. It's like
Yes, right? 123 over 1,000, right? Okay. What was special about or what that decimal that told you to write as a fraction? close, it doesn't, what's special about it is that it terminates, right? It doesn't go on forever. If the decimal terminates, you can write that thing as a fraction, because all you have to do is write it, like number over some power of 10, right? Like 0.123, you can write as 123 over, some power of 10, 10 to the third, right? As long as that decimal terminates, it's a rational number. Okay, everybody's good there? That which should make sense, right? 0.25, 0.1, all these things like 1/10, 1/4, that we're familiar with, all for sure fractions. Now, the other class of decimals that we can write as rational numbers are the ones that, now Cammie, it's time for repeats. So like 0.3 repeating is 1/3. And the key there is that it goes on forever, but there's a pair, right? Or 1/6 is 0.1 and then 6 repeat, right? Those are examples of things that are also rational numbers. So what kind of decimals are not rational numbers? They have to go on forever, but they cannot repeat. What's an example of a number like that? Pi. Excellent. That's your number one example. Another. It's another algebra 2 number that we don't give a number to. E. Wonderful. Yup. And then your next major class are going to typically be radicals. So like square root 2, square root 3, not square root 4, because that's just 2, but like square root 5 and square root 6. Those are all examples of not rational numbers. What do we call those things that are not rational? Irrational. Yes, good. Everybody's good? Okay. And then our final class of numbers that we'll talk about are the real numbers. What are the real numbers? Anything you can write as a decimal. Anything you can write as a decimal. What kinds of things can't you write as a decimal? Things with eyes in them. Right? The imaginaries. Right? Because you can't do that.
Anything but imaginaries.
Yep. It's anything you can write as a decimal. Right? Like whether it's repeating or not, whether the decimal is infinite or not, it doesn't matter. It's still a real number as long as there's no I tacked on to the end of it. Or have a plus something I at the end of it. A little aside that is not something I would expect you to know. Which one do we think there's more of? Natural numbers or integers? Why would you say integers? Because it includes things that the natural numbers doesn't. Would you be surprised, though, that I told you, what if I said that I can create a function that pairs up exactly one natural number with every single integer? Then they'd have to have the same amount of things, right? You can do that by just mapping the odd natural numbers to the positive integers and the negative natural numbers to the, and the odd or the even natural numbers to the negative integers. And lo and behold, that map is 1 to 1 and onto. That means they have to be paired exactly 1 to each, which means they have to have the same number of stuffs. Weird. Infinity is weird, but that's an example. What about, so natural numbers and integers, we can say kind of they have the same amount of stuff, right? The math term for that is they have the same cardinality. What about integers and rational numbers? You have the same nested thing, right? Every integer is a natural number. But is there a way to set up like a pairing right, and pair up every integer with every rational number so that it really means they have to have the same amount of stuff. This is not trivial. You can do this. They are the same size sets, or have the same cardinality. The math or the argument to do this is quite complicated, well beyond the scope of this, and not something you can just like prattle off like, oh, send the odds to the negatives and the evens to the positives, and we're done. That pairing is not obvious. You end up having to build like a grid and doing like a diagonalization argument. The mathematician Gregor Cantor is the one that made that proof. Not that any of this matters. How about rational numbers and real numbers? Here is no. These are fundamentally different size things. They have
more real numbers.
There are more real numbers. It's a different order of infinity. As you know, infinity has different orders of magnitude. So they are different orders of magnitude. There are, in fact, just the irrational numbers has this different order of magnitude than the rational numbers. None of this is important to this class. This is all just for fun. Because it's interesting.
Did you watch the Netflix documentary like about infinity? There's a cool one that just talks about infinity. I think I started with it.
High five to you. Way to go. What do you watch on Netflix? Documentaries about numbers. You know. I love it. All right. Any questions on this? Okay. So if I say we have the number 5/4, what sets does 5/4 belong to? Rational. Real. Everybody agree? Okay. If I have the number -7, what's that a number of?
Real.
Integers, real.
C minus.
C minus. You're missing one though.
C.
Rationals.
Oh, rationals.
Every whole number is a rational number because you can just write it over 1. Right? Yeah. Square root 7.
Rational.
Not rational.
Wait, no.
Just reals. Right? You can't write the square root of 7. That's a fraction. Everybody feel okay? And these feel like test questions, right? Or because this is like, what set is this a member of, right? Okay. All right. Let's go to the next one. So here's a picture to help you visualize this nesting, right? That the natural numbers are inside of the whole numbers, are inside of the integers, inside of the rational numbers, which are paired with the irrational numbers, are all parts of the reals. So that's a nice visualization. If you're a pictures person, I'm a pictures guy. I like visualizing something. This does a nice job of capturing the nested relationship between these different number sets, which is a really common idea in all of mathematics, right? We start with an idea, and then we say, okay, what can this do? I want something then that includes everything this is, and then a little bit more. And then I'll take that and a little bit more, and so on and so forth. And this is really common approach. You start with something easy that you can handle, and then you see, okay, can I generalize from there? And you can come up with something a little bit more robust, a little bit more general. And you say, okay, can I generalize from there? And you just keep working your way out until you have something that works kind of for everything. Everybody cool? That was the first section. Just like, can you pick out what kind of number something is? Not hard, right? Next thing we're going to talk about are SI units. SI units are examples. Like grams and meters and liters, right? Like the things that you'll have millicenti, deca, or deci, deca, hecto, kilo, the prefix is attached, right? SI, I think, is an abbreviation for System International or whatever. It's a French term. Nobody. So if you have like some base quantities like length or mass or time or whatever, they have a base SI unit like meters or kilograms or seconds. This is not something you'd be expected to memorize. Like, what's the base unit for these different measurements? Like, that's not important. Just doing this as an illustration. What you should be familiar with are like, milli, centi, deci, deca, hecto, kilo abbreviations. Like, that should be okay. Right? You should remember that from your science classes. I hope at this point you've seen that probably a number of times. And if not, like, mostly it's milli, centi, kilo are the ones that really happen. Now, when we talk about temperature, there's 3 temperature scales that are commonly used. There's Fahrenheit, which is what we use here in America, Celsius, what everybody else uses, and then Kelvins, which is what scientists use. So we have 3 conversion scale, or 3 conversion formulas here to go from Celsius to Kelvin, from Fahrenheit to Celsius, or from Celsius to Fahrenheit.
These will be given on like the formula sheet.
Yes. Yep. Again, the good question Rocco asked, do I need to memorize these formulas? No is the answer. You just need to be able to use them. They would be given to you on a test or a quiz or a classwork or whatever. Yes?
Are we still gonna have sheet for our test?
No half sheets on here, but anything that's formula will be given to you. Okay, the IB doesn't believe in memorizing formulas, so you don't have to worry about that. Okay. Everybody okay? Does the boiling and freezing points of water matter? Do I need to know this? What do you think? Not memorized. Sometimes it's helpful that you recognize that, like, oh, 212 degrees Fahrenheit, that's the boiling point of water at sea level. But really, it doesn't. Right? Like, that's just because you're smart. As mentioned before, the prefixes for these SI units, again, the expectation is that you're familiar with milli, centi, deci, deca, hecto, kilo, just those 6 surrounding the base unit, and each of them is 10 more, or a factor of 10 more than the previous. Thing to be careful is that we have derived SI units, right? So like area is meters squared, or volume is meters cubed, or velocity is meters per second, or whatever. We're going to take the product or quotient of 2 SI units. The place where you have to be careful of then is in converting, say, square meters into square centimeters. Right, we'll do an example of that here soon. It's not in the PowerPoint, I'll do it by hand or whatever, just to illustrate what's going on. Again, do you need to memorize any of these things? No. You just need to be able to deal with it when you see it. Okay, so let's look at an example. So for just a linear unit, say I want to convert 10 centimeters into inches. I start with the quantity that I have, the 10 centimeters, and I multiply by the conversion factor, right? We know that 1 inch is 2.54 centimeters. You guys remember hearing this before? How many of you would have been able to remember that conversion factor offhand? Typically they'll say with the SI units where it's like everything's a 10 or a factor of 10. But the English, like most of us are more familiar with inches than centimeters as far as like picturing what this is. I don't know. I remember all these things. So the key is if you have a derived unit, like you have 10 centimeters squared, you need one conversion factor to cancel one of the centimeters, and then you need a second conversion factor to cancel the other centimeter to leave you with inches squared, right? Because you have inches times inches on top to get into inches squared. This is a really common mistake that I see students make in converting units, specifically with these derived units, is that you don't apply the conversion factor enough times when you have like a unit to a power, right? If it's a square unit, you're going to need the conversion factor twice. If it's a cubic unit, you're going to need the conversion factor 3 times, and so on and so forth. Is everybody okay with that idea? I'm going to leave this here for a minute. Just emphasize again. Be careful with these derived units if you're asked to convert units. You have to be sure that you're using the conversion factor the appropriate number of times. Okay. And here's the cubic example where we use the conversion factor. Just like we said, right? What do you guys think? So far, so good? No big deal, right? This is like first day of science class in 9th grade again. You know, it's like in school. If it wasn't the first day, it was like the first month. Okay, well, fair enough. The next thing we want to do is talk about approximation and error. So the standard in this class is you're going to write your answer. So 3 sig figs. Well, your answer should be exact, or 3 sig figs, unless otherwise stated. Right? Like the question could say round to some other spot. Right? Like if you're dealing with a question involving money, they'll probably say round to the 100. Because typically money is dollars and cents. Right? Whenever you do a present a rounded answer, though there's some error taking place, right? So if I say that my rounded answer is 10, that answer could have been as small as 9.5, right? Or as large as 10.49999. Both of those would round down to 10. Does everybody agree with that? So this is kind of what we're going to be talking about here. So rounding, it's the process of estimating the value for extremely long numbers, right? Very common to do. The degree of accuracy is, yes,
Can I answer the question?
of course, yeah. There's passes hanging on the wall, just grab one, put it back on your return. The degree of accuracy basically describes the extent that the number is rounded. In this class, we're going to use the typical rounding instruction where if the digit that you're looking to round at, you look at the next digit to the right. If that digit is 5 or more, we round up. If that digit is less than 5, we round down. Right? The same kind of rounding we did in like elementary school when you were introduced to this idea. Everybody's okay? Unless otherwise stated, right? There could be a story problem in which, like, you want to know how many people you can fit to a car, right? And your answer is 3.25 or 3.75. Your answer of how many people fit in this car should be 3. You round down because you don't have space for a whole person. You can't have, right? If you try to round up and squeeze in that fourth person, you don't have this full space anymore because you can't like quarter a person. I mean, you could, but it'd be really messy. I was hoping you'd get a laugh out of that. All right. All right. Significant figures. As I mentioned, the expectation of this class is when you report your answer, you can report an exact value or an answer rounded to 3 significant figures, right? Now, I think everybody, I'm guessing, has done a science class in which you talked about significant figures at some point in your career, right? What's the point of a significant figure in a science class? Why don't we just say like round everything to 2 decimal places? A little bit more to it than that, though. Not just precision and accuracy. What the significant figure does in your science class. Where do these numbers come from that you have in a science class? You had to measure them, right? And when you measure them, you use some kind of a tool that allows you to read accurately up to a certain measurement, right? So if you have a yardstick that can read up to the 1/4 inch, you report your answer rounded to the 1/4 inch, right? Or if you're looking at a graduated cylinder that can read to the milliliter, you report your answer rounded to the nearest milliliter, right? Now let's say you take your 10 milliliters and you divide it by 3. You need to report your answers to one significant figure in chemistry because if you reported your answers like 3.3, it implies the tool you used was accurate enough to read to the 1/10 of a milliliter when it was not, right? That's what the significant figures are doing because you should not be able to create a more accurate measurement by adding and subtracting and multiplying and dividing, right? Like that all of a sudden you can't get a better measurement than what you use, than the tool you use to take the measurement with. And really the least accurate tool you use to take the measurement with. Does that make, I think when you look at it that way, like the rounding for the significant figure rules makes so much more sense, right? If I have like 10.4 and like 4.56, my least accurate measurement was the 10.4. So I round to the 10th place when I add those two numbers together because it's rounded to the least accurate measurement. Right? When I multiply or divide, I just have the same number, I round to the same number of sig figs as the original number. Right? Because it's the same, I should have the same level of accuracy when I started. If I had 1 sig fig and I divide it by 5, my answer should have 1 sig fig. Does that make sense? Okay. So that's kind of the why of why you need significant figures, what they do, what they communicate. What are the rules for when we know a digit is significant or not? What's the one for, okay. What are the easy digits to tell are significant? Non-zeros, right? All non-zero digits are significant. Everybody agree? The zeros are the pesky ones. Okay? The easy zero to pick out as significant is when it's sandwiched in between 2 non-zeros, right? Or I should say 2 significant digits. That's probably a cleaner way of saying it, right? The sandwich, usually most kids remember that one. Leading zeros, so like 0.005. Leading zeros, never significant, right? The bugger is trailing zeros. When are trailing zeros significant? If they occur after the decimal point. So like 5.0, 2 sig figs because the zero's after the decimal point. 50, 1 sig fig because the zero is not after the decimal point. The only exception is if you wrote 50 and then decimal point, that would make the zero at the end significant. Right? That's the one tricky one. But the decimal is what makes the zeros at the end significant. The only exception for that is if you have leading zeros after the decimal point, right? Like 0.005, still 1 sig fig, because those are all leading. You only have the trails after the decimal, right? So it's only trails that we have to worry about after the decimal is significant. So like 10.0 has 3 sig figs. The 0 on the 10 is significant because it's sandwiched between the 0 after the decimal and the 1, right? Is everybody feeling okay on this? Again, the zeros are the only hard parts. If it's just, if they're non-zeros, it's easy. They're all significant. Okay. So this is the same rules we just kind of discussed. Again, I tried to talk my way through it and then do it after. One thing worth noting, again, oftentimes an issue for students, is the only rounding that should be done is on your final answer. You don't want to round intermediate steps. So if you're doing something on your calculator, you want to keep the entire decimal all the way through to the final answer. And we'll show you guys easy ways to do that using your calculator as we kind of go on. It'll be a little bit of calculator education if you're not particularly good at using and manipulating numbers inside of your calculator, or storing numbers and saving them in your calculator, or recalling numbers from a different line of calculation in your calculator. We'll show you how to do that and have some practice there to get a little bit better at that. But that's an important one, right? Because if you, like, I takes, like 10 divided by 3, I round my answer to 3.3, and then I divide that by 3, I'd say my answer is 1.1 rather than 1.11, which would be the answer rounded to 3 sig. Right? You get two different answers because you rounded to 3. Does that make sense? So when you talk about a rounded number, oftentimes you want to discuss its bounds. So it's like the amount of error attached to that rounded number, which is kind of like when I say we rounded a number to 10, we said that number could have been as small as 9.5 or something as big as, or something less than 10.5, right? That's what we're talking about when we talk about bounds. Right? So typically when we'd write that, we'd write it in this fashion. So remember, the smaller number is always going to be a less than or equal to, but the bigger number is always going to be a strict less than. Everybody's okay with that? So again, making sure those inequality symbols, you have the or equal to on the right, on the correct, I should say correct end of that statement is the common mistake there. But it's usually not hard because you remember, like, oh, at 0.5 we round up, but less than 0.5 we round down, right? But again, if you think about the actual mechanic of what you do when you're rounding it, it should make sense with the inequality, or which side the equals goes. Everybody's okay here? Oh my goodness, guys. All right. And then where those bounds are can change depending on the digit that we did the rounding at, right? So let's say that we have 5 as our answer, but we rounded it to the tenths place instead of the ones place. So where's the error going to be at? In the hundredths place, right? So the smallest this could have been would have been 4.95, and the biggest it could have been would be 5.05. Or well, I should say less than 5.05. Right, so if you round to the tenths, your error is going to occur in the hundreds. If you round it to the hundreds, your error would occur in the thousands, and so on and so forth. Always just one digit to the right of wherever the rounding occurred. Does that make sense to you guys? I know it's kind of wordy in here, but it's like if you think about, okay, I rounded to the 10th, so what number did I look, what place did I look at? Oh, I looked at the hundreds, right? Just one space to the right. And then it's the same thing, like minus 5 and plus 5 on that digit, whatever. Is everybody okay? Yeah, this should feel pretty, again, if not familiar, but like simple enough of an idea, right? There's nothing complicated going on here. We're doing no computation. We're just kind of like, oh, what does this rounding number really mean? It could have been anywhere between here and here. Okay. Now, when you make a measurement, there is some actual correct answer to that measurement. Or when you make a measurement to calculate a value, there is some actual correct answer to that calculation, right? The difference between your measured value and the actual value is called the percent error, which is just the difference between the actual and the exact divided by, the approximate and the exact divided by the exact. And then you take the absolute value because you don't have a negative percent difference and multiply by 100 to turn it into a percentage. So everybody used this calculation in a science class, I'm guessing, at some point. If you ignore the absolute values and you get a negative percentage, what does that mean?
Even more error.
Well, it means that your measurement was less than, it was an underestimate of the actual value, right? If your percent error is a positive value, it meant it was a overestimate. It was bigger than the actual value. Everybody's okay with that? I feel like that's a homework question along the way somewhere, where it's like, oh, if you think about that for a minute, like, sure, I would have come up with that, but like, you know, it's maybe not super obvious at first read of like, what the heck are they even asking me here? That's all we're talking about, right? It's simple enough of an idea, but you have to think about it for a minute. Oh yeah, here. So this is the statement that I had, right? So again, if you ignore the absolute value, negatives mean that it was an underestimate, positives mean it's an overestimate. When you report a percent error, though, it's always a positive value. What do we have left in class? Is it 10 minutes left? Is that where we're at? I think it is a good stopping point, right? Don't you guys?
Yeah.
Okay. I agree. I'm not in too big of a rush.